Hi guys, in the series of lecture based on complex analysis, volume 2, I just discussed up to the last lecture, that is in calculus of residue. I was discussing how you can solve real integral after transforming into the complex form by using Cauchy's residue theorem. And I told you what is Cauchy's residue theorem. That is simply known as also a residue theorem. If we have integral of fz dz, then I told you this will be equal to 2 pi into the sum of residues. I introduced this theorem, I stated this, and then I proved. And also I took up one example today of based on this. Today I will take two examples. Real integral that can be solved by using, that is real integrals solved by contour integrations. In which I discussed up to the last lecture, first case, if we have integral, first case I discussed if we have the integral I over 0 to 2 pi based of complex form sine theta. Simply this is based on integrated containing sine theta, cos theta, etc. Then I told you these can be converted into the complex form by using Euler's formula, that is z equal to ei theta. Ei theta means cos theta plus I tan theta. Then you know that 1 by z is e to power minus I theta, that is cos theta minus I tan theta. Then I told you from this formula, and we take a unit circuit mod z equal to capital R, it will be transformed, it will be reduced into a complex integral, and then we take a complex function fz and find its pole, and then we find a residue at that poles which lie in that unit circle, that region of integration, and then by using residue theorem we can solve such type of integral. And also I took one example based on the sine theta and cos theta, and also some real other integral that can be solved by this. In today's lecture, I will take up such real integral containing algebraic functions, a rational type and other type, that can also be solved by using residue theorem after changing that integral into the complex form. So first, like that, if second case, if we take integral 0 to infinity f1 of x and f2 of f dx, like that. If there is a function of rational function, if we take negative limit minus infinity to infinity, if such type of integral, those can also be solved by using a residue theorem after converting this. How? If we take, what is the process, what is the method? If we take, let us take fx equal to f1x of f2f. If we take this rational function as a function and consider integral c of fz dz, right? This is directly converted into complex integral by changing the x by z. That is integral c fz dz, where c is where c is curve consisting, actually this is c, curve consisting upper half of the circle, that is, and this is real axis, this is original, this is imaginary axis. So c is the curve consisting upper half of circle consisting upper half of the circle CR of mod unit circle mod z equal to R and part of real axis from minus R to plus R, minus R to plus R, and this is CR, right? This is this, and here R is very large. Here R is very large. That means R tending to infinity, right? And poles lie in this C. Poles of Fz, we take poles lie. Now, pole of Fz lies inside C. Pole lie inside C. Then by residue theorem, integral C of Fz dz equal to 2 pi into sum of residue, right? This is by residue theorem, and here actually this integral converted into in this form like that. Now if we take integral C Fz dz, this will be equal to, because C is containing two parts. One is CR, that is the upper half of the circle mod z equal to capital R, and second is the part of real axis lying between minus R to R. So this integral will be in two parts. One is minus R to R of Fz dz, this one, and plus integral over CR of Fz dz. Actually this integral is of two parts, right? And this is from here by residue theorem. This is equal to this. So we have an equation like that. If this integral minus R to R Fz dz plus integral CR Fz dz and left hand side integral is equal to 2 pi I into sum of residue. Now we take this is as first equation, right? And now in which we take these two integrals separately, we solve on the basis of conditions here, because we are taking large circle, means capital R is large and CR is part of this. So in this if we take this integral on CR first integral one, then here mod z equal to capital R. If you change it into polar form, then you know that z equal to AR I theta, then dz equal to R I E I theta d theta, right? And for circle, limit from theta equal to 0 to 2 pi. These are the changes, these are the transformations by which this integral CR becomes f of Ri theta. This integral number 2 of left hand side of equation 1, that is Fz dz equal to integral 0 to 2 pi f of R ei theta, and dz means R I E I theta d theta. This integral will be converted into the polar form, and we can solve this. And because R is large, always this will tend to 0 as R tending to infinity. This is the this integral. And now if we take equation number 1 and taking limit r tending to infinity, then this will be 0, and we have now if we take limit r tending to infinity in equation 1, we get minus infinity to infinity fz dz plus this integral becomes 0, and then right hand side 2 pi I into sum of residues, right? This becomes 0, and now calculate the poles and then residues values, and then we get the required integral. After changing this z by x, then we get required integral minus into infinity fx dx equal to value of this. This is the method by which you can solve given real integral by using a residue theorem after transforming them into the complex form. So first I will take up an example based on this, how you can solve such type of integrals. Now, numerical example. If we take numerical example, evaluate integral 0 to infinity cos mx upon x square plus 1 dx. Actually, this is the function, right? We have to solve this by using Cauchy-Reizl residue theorem. So here we can take for solution, we can take fz equal to cos mz upon z square plus 1. By the given function, for the given function, we can take fz as this. So consider integral fz dz over c, right? And take c. What is c? Again, similarly, c is a curve containing half part of the semicircle and part of real axis between minus r to capital R, right? Let C be curve containing upper half CR of circulate large circle, mod Z equal to capital R, where R is always tending to infinity, and part of a real axis from minus R to R. Then know that C equal to CR, then this is real axis minus R to R and plus CR, right? And here Fz is this. So for Fz, poles, that is Z square plus minus 1 equal to 0, then you know that poles mean the points at which Fz approaches to the infinity, tends to the infinity, then we put Z square plus 1 equal to 0. Solve this, we get Z equal to plus minus I. And from here we see that Z equal to I is only pole lying inside C, that is on imaginary axis from here. This is I. This is the pole which lying inside C. Now calculate the residue at that pole by formula. We know that It's a simple code. So residue at z equal to I is formula limit z tending to I, z minus I of fz, that is cos mz upon z square plus 1. This is the formula for residue. Cos mz here we take actually for this function, because cos mz is the real part of the e to power iz. So we consider this fz is e to power minus iz upon z square plus 1. Please, this is the point. Whenever the function containing a cos mx or sin mx, then we choose a function in form of this, that is I mz, because by Euler's formula, cos mz is the real part of this. If in here sin mz, then we can save from this, and in last we take here real part. In case of sin mz, we take imaginary part. So we take e to power mz. So your function is e to power I mz, and we can factorize this as z minus I, z plus I, z minus is cancel out. If we put value, then e to power minus m, if you put z equal to I minus I square, and from here that is 2I. Z minus I is cancel out. So this is the this is the fourth. This is the value of residue at this. So by Cauchy's theorem, integral c of z, if we calculate this integral by Cauchy's theorem, then what will we get? Therefore, by residue theorem, integral c of fz, that is integral c of e to power I mz upon z square plus 1 dz equal to 2 pi I into sum of residue, here only residue is only 1, e to power minus m upon 2i. 2i is cancelled out, so this is pi times e to power minus m. This is the value of this integral. And now we also can take integral c fz dz, because c is considering 2 curve, so this is equal to minus r to r first fz dz plus o integral or cr fz dz. And we have already calculated value of this integral pi e to power minus m. Now substitute this value, so we get minus r to r fz dz plus cr fz dz equal to pi e to power minus m, and take this as equation number 1. Right? Integral will be transformed, will be reduced into two parts. You have already calculated this integral left hand side by the help of residue theorem. The value of this integral is this, so this is. And now calculate these two integrals under these conditions. What is the condition? A pole is lying inside C. C is a curve containing half part of semicircle mod z equal to capital R and part of real axis lying between minus R to capital R. Now calculate this first for this integral over this. On CR we have mod z equal to capital R. This is the equation of circle, and if you open this in polar form, this is z equal to r ei theta. So this is dz equal to I ei theta d theta, right? And theta lying between 0 to pi for semicircle, not pi, because this is semicircle. So theta lying from here 0 or minus pi. So integral CR fz dz is equal to integral 0 to pi f of, that is r I e theta, dz is I ei theta r d theta, right? this is the value. This is R. Now, if you calculate this is value of function. If you calculate 0 to pi e to power I theta, you can calculate this by value of this from here, because fz equal to e to power I mz upon z square plus 1. Right? So f of r a theta means e to power I m z means, if you substitute the value of z, so if we take the modulus value of this expression, this can be converted. If you take this in modulus value and then take the limit, because r is large, means r is always approaching to the infinity. So if we take this by formula, because this is before this, if we take this, this is basically integral CR fz means e to power I mz. Take another simple method. It is very simple method. Then, if we calculate its value through modulus and then take limit, to that will be, I think, very easy method and very short method. If we take mod of CR fz dz, then you know that if we take limit inside this integral, CR means this is 0 to pi, that is mod of e to power I mz mod of z square plus 1 mod of dz. And you know that mod of EIX is already equal to 1. And further, mod z square plus 1 is less than or equal to mod z square plus 1. This is further. If we take this, then if we take mod, this is 0 to pi, this is 1, this is mod z square plus 1. Mod dz means from here r mod I is 1, mod I theta is 1, theta. This is, and if further you calculate this, mod z is equal to r, this is r upon r square plus 1, and theta is 1, we get 1. Right? R upon r square minus 1. Then this tends to 0 as we take the limit L tending to infinity. And this implies that integral CR fz dz equal to 0 as r tending to infinity. Right? Now, we have value of this integral when r is very large value. As you assume that mod z equal to capital R is a large circle means r having very great value, very large value, simply r tending to infinity. So now take limit as r tending to infinity in equation 1. We get first integral is minus r to r, so that becomes minus infinity to infinity f of z dz. Second integral is 0, and third value, and that value is e to power minus m upon pi, and this is upon pi. This is pi into e to power, sorry, pi into e to power. That is the value of first equation, and this is equal to 0. And now simply this is definite integral. We can change that minus fx equal to pi of e to power minus m. This is the constant value, and because it is real integral by property of definite integral, it becomes 0 to infinity 2 times fx dx equal to pi into e to power minus m. Finally, you get your required integral 0 to infinity fx dx equal to pi by 2 e to power minus m. Right? This is the final answer of the integral. So this is a type of real integral, and those can be solved by using a residue theorem. you can solve this. And similarly, some other type of example that is solved by Residue theorem, those are known as intended theorem, because here we take this curve C as a region of integration in which only pole line in this part, in this portion, in that portion that is containing, that is bounded by arc of semi-half circle and real axis. But pole cannot lie in such cases on real axis. If we take, in some cases, you see that pole will lie on the rear axis. Such type of integral are known as intended integral. That is the last application of this intended integral or intended contour integrals, in which if we have a function and pole lie on the rear axis, means if we have solved the integral this, and here pole lies on rear axis at origin, then we indent this origin also. Means we take we take a small circle around origin, and now this is the region. And now we discuss on this region how can you solve this. Means now this this part C fz, and we take another integral that is very another part of this, another semi upper half of a semicircle of a small circle, small r. Then we take this region, and this region is naturally a region in which no other pole lie. So we can say a function is analytic in this region. So by using Cauchy's integral theorem, you know that if any function, you know that the Cauchy's integral theorem states that if any function is analytic in a closed region, then integral over that region is equal to 0. By using this, if we take an example, then this is very clear. What is the method? Suppose question is evaluate integral 0 to infinity sine mx upon x dx. Suppose we have to solve this, right? Same concept here, sine mx. So we take function fz equal to naturally e to power I mz upon z. For this integral, we have to take this one, right? Means now for this, consider integral c of fz dz, means integral c e to power I mz upon z dz. So you see that here pole is at z equal to 0, right? That is on x-axis, that is the origin. Now for avoiding this pole, we consider let mod z equal to r be a large circle, and large circle intended at z equal to 0, and let mod z equal to small r be a small circle, right, with around at that intended z equal to 0, right? Then here we see then C is a region, right? C is the region bounded by CR and CR upper half, and real axis as C is if we take this small r, then part of real axis minus r to small minus capital R to minus small r, then C small r, that is minus CR, because this is integral way on clockwise. This is CR. If we take this is same minus CR, then this is plus CR and this is plus CR. Then again part of real axis from this one plus R to capital R and then plus CR, right? And so our integral is therefore integral CFZ dz containing 4 parts. One is minus capital R to small r fz dz plus integral over CR fz dz plus integral small r to capital R fz dz plus integral over CR, right? This is in this, right? And left hand side integral is always 0 because fz is analytic, and we take solve this. This integral is equal to 0 by Cauchy's theorem, and now take this, solve this similarly method by using r tending to 0 and capital R tending to infinity. Solve these things, then these two integral combine, and this will be equal to this and this again equal to 0, and then you can solve and find out the integral, intended integral, right? Solution is given, and then you will get this formula by using residue theorem, because here the function is analytic in this region, that intended region, then this, okay, you can solve this, and these are the simple applications by which you can solve contour integrations by the help of residue theorem or complex Cauchy's theorem. And this was the part of your second volume of complex analysis, and according to your curriculum and syllabus of your university, your complex analysis theoretical part is up to this topic in 2 units. That is complex analysis volume 1 of first module, complex analysis of volume 2 of second module. And now up to this lecture I have finished complex analysis completely. And now from next lecture I will start your third unit, that is the integral transform, third and fourth unit. Integral transform consisting third and fourth unit, in which 2 chapters, 2 modules are given according to your curriculum. One is Fourier transform and another is Z transform. So from next lecture I will start Fourier transform. Okay, thank you.